It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and with Dave Ansell. Hi, Dave.
Hi there.
Now, in the programme this week, we're going to be finding out how researchers have come up with a way to make softer ice cream, yum yum. Also, how scientists have grown a new heart in a laboratory dish, and multicoloured X-rays, how the imaging equivalent of black and white television is going to enter the Technicolor age, and this is going to make imaging and spotting various diseases much easier, we think. That's all on the way. Dave.
Thanks, Chris. Also coming up in this week's Question of the Week, we're trying to solve a problem that just won't go away.
I want to know how the boomerang works and what's the principle behind that.
We'll be coming to that. We're coming back to that later in the show. Plus, our technology correspondent Chris Vallance has been finding out about the next generation of must-have gadgets on display recently at the LA Consumer Electronics Show, including this wacky item.
There was a new take on that with a picture frame where you could actually had a mobile phone number, so you could send the pictures to it. Now, I must admit, the evil part of my brain was thinking about all the pranks you could play.
I'm not sure what I would text into that picture frame, but it certainly sounds like a lot of fun, and you could be quite evil with it, couldn't you? Thank you very much, Dave. Now, it is, of course, our Science Q&A show this week, so if you've got a science question for us, which is anything science, technology or medicine, do get in touch. Email us, chris@thenakedscientists.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Well, let's kick off, as we always do, with a look at some of this week's hottest science discoveries, including one that's really not hot, it's cool.
Now, scientists have developed an edible antifreeze that possibly surprisingly actually makes ice cream taste better. Now, ice cream is a complex structure made up of fats, carbohydrates and water, and as the name suggests, the water's in the form of ice. Now, really nice, smooth ice cream, the really posh stuff, has got really small ice crystals that are less than 20 microns across. That's 20 millionths of a metre across. They're made really small by freezing it very, very fast so they don't have time to grow. They also add some long carbohydrate, sugary molecules to inhibit these crystals' growth. But as you may have noticed, if you've ever let ice cream warm up and melt and then freeze it again, it goes really gritty and horrible, and you get almost sandy texture.
It's crunchy, isn't it? It's
really crunchy. It's not what you want from your ice cream. Now, Srinivasan Damodaran from the University of Madison has been working on this problem by his partially digested long gelatin molecules with an enzyme found in papaya juice called papain. This forms short protein molecules which seem to interrupt the growth of these ice crystals and keep the ice cream really smooth even after you've warmed it up and refrozen it.
How does it work?
They think it kind of gets in the way. It's kind of very strongly attracted to the water, and so it gets in the way of these crystals growing. So it forms lots of small ones rather than one big crystal.
About 4 or 5, 6 years ago, Unilever, who everyone knows about the company, they make a lot of ice cream, and they were searching around in the Antarctic and the Arctic for organisms that survive at very low temperatures, because their argument was if these animals have got their own natural antifreeze and it doesn't harm them, it probably would make an ideal thing to put into ice cream. And I think they found some proteins. So how does this differ from that?
Yeah, I think they actually ended up putting it in genetically modified yeast and then growing it, and then I'm not sure whether they actually put it into ice creams or not. Well, it's just making it from bog standard gelatin, which is cheap, which you can just buy from old meat, which has gone down, which you don't need. You boil up the gristle and you get gelatin out. And he was actually interested in what was going on, so he looked at the molecules after he chopped up the gelatin, and they're actually a very similar shape to a molecule very like the one you were talking about. They're actually found in things called snow fleas, which are little insects which live in the winter in northern latitudes, and they keep active all the time, and they have their own natural antifreeze. So this
is similar to the Unilever principle, except these slightly bigger snow fleas they have a molecule quite similar to this.
Yeah, and this chopped up gelatin just happens to be very similar and works the same way.
And is this actually being employed in making ice cream, or is it just theoretical at the moment?
I think he's just done the experiments recently. It's going to take a few years before it can get into
Problem
ice
is,
cream.
it's still not vegetarian friendly, though, is it? Because if it's got gelatin in it, then presumably vegetarians are not going to want to eat it.
I guess so. For a while, at least, there's going to be a choice whether you want the vegetarian ice cream or the ice cream which doesn't go gritty when you melt it. There'll have to be a choice for those vegetarians.
So they still have to suffer no matter what, these poor vegetarians, don't they? They can't have it both ways: smooth ice cream and ones that they can eat. Anyway, talking of eating ice cream, it might taste great, but it won't necessarily make you live a long time, and that's because it's obviously got a lot of fat in it. But scientists have now got 4 things that you can do to make yourself live longer. This is the research of Professor Katie Kaur. She's a researcher based at Cambridge University, and in the mid-90s, she was recruiting 20,000 men and women who were between the ages of 45 and 71, and they were trying to put put their finger on what the factors of a lifestyle are that make you live longer. And they've identified 4 things which, actually, if you do all these 4 things, you will live 14 years longer on average than someone who doesn't do any of these things. So all the people who took part in their study answered 4 simple questions. Do you smoke? If the person answered no, they got a point. Do you drink moderate amounts of alcohol? If the person answered yes, they got a point. Do you have 5 portions of fruit and vegetables every single day? If you answered yes to that, then you got a point. And they measured that by, also confirmed it by doing blood tests to see if they had enough vitamin C in their blood, which showed they weren't lying. And the other point that they did was exercising. If you took moderate amounts of exercise, then that scored you a point as well. And when they analysed the data in 2006, so they followed up how long the people they'd enrolled in the study lived for, they analysed it in 2006 up until the present day, and they found that people were, with a score of 0, were 4 times more likely to die over the subsequent 11-year period than people of the same age that had 4 points. And looking at this another way, if you have 0 points, then you're as likely to die as someone who's 14 years older than you with 4 points. So in other words, you can make yourself potentially live 14 years longer than you would have done otherwise if you don't smoke, drink moderate amounts of alcohol, take a bit of exercise and eat 5 portions a day of fruit and vegetables.
Wow, that's what everyone tells us obviously actually works, which is nice to know, I think. Now, colour X-ray images may help doctors identify damaged tissue. Now, X-ray images are traditionally in black and white, all the ones you've ever seen, just black and white. They're made by actually shining X-rays through some tissue and then looking at the shadow of the X-rays. So things like bones will stop the X-ray light going through and cast a shadow, which is what you see as white on the images. And in fact, even the 3D posh CAT scanners work on the same principle, but just taking lots and lots of pictures from different angles and putting them back together using a computer. But X-rays are a form of light, so they can have lots of different wavelengths in the same way that visible light can have lots of different wavelengths, which we call colours. And we detect lots of useful information about the world from the colour of light that's reflected off it, so you'd have thought the doctors could do the same thing with the colour of X-rays. Now, Robert Cernick in Manchester has built a 3D scanner that will actually tell you what colours of X-rays are being reflected from any part of the body inside you. Send a beam of X-ray through the object and looking from the ones which bounce off and measuring the wavelength of these X-rays and moving the detector around, you can build up a 3D picture of what's inside the person. However, it's going to be still very, very early days because he's made a beautiful image of a 5mm by 5mm cross, and it took him 3 hours. And I've seen a photograph of this cross, and it's kind of looked blackened and brown from all the X-rays going through it. So it's going to be a few years before it actually works.
So just to summarise, what you do, instead of sending X-rays at just one energy, one wavelength through, say, a person, you could send X-rays of different wavelengths, different colours, if you like, through the person, through their tissues. Different tissues are going to interact with the X-rays in slightly different ways. The detector could pick that up, and this means that you could get much more information about what tissue the X-rays have gone through, and that means you could potentially begin to spot various diseases and things much more, well, with a much better resolution than we can at the moment with just looking in black and white.
Yeah, exactly right. All that more information you get in Technicolor.
But there's a little way to go because they've managed to image a 5mm by 5mm area. Why is this not being done already? Why is it so difficult?
I think the detectors are quite difficult. He's looking at getting some... At the moment they're using silicon detectors, which are incredibly inefficient. They only actually absorb about 1% of the X-rays which are coming through. And you're also only looking at the X-rays which actually bounce off something going through. So you're looking at a very, very tiny amount of the X-rays going in. He's trying to get some higher tech sensors, which should speed it up by a factor of about 100.
Because I thought scientists were trying to get away from using X-rays because they were ionising radiation, they can damage tissue, and things like magnetic resonance imaging, MRI, by virtue of not using X-rays, is safer.
That's entirely true. So giving someone a really, really high dose of X-rays is probably going to put them into a worse position than they are already.
Because one chest X-ray is about 4.5 days of solar radiation. So in other words, the same exposure you get from a chest X-ray is equivalent to knocking around in the sun for a few days, just on a beach or something. But if you have a CT scan of your whole body, it's about 4.5 years of radiation. So it's pretty big doses. So I know what I'd rather have at the moment if I had a choice.
Indeed.
We're talking about getting ill and repairing things. There's an amazing piece of work which has been published this week by Doris Taylor and her colleagues. She's from the University of Minnesota, and she's teamed up with some people at the University of Harvard in Boston as well. And what they've managed to do is, for the first time in the world, grow a whole organ outside the body in a dish in the laboratory. And what they've done is to grow a new heart. and you think, this is incredible, how have they done this? And the way they've done it is to start with a defective dead heart and use that as a template or a scaffold to repopulate it with new cells. Now, let me explain. When you have an organ, like a heart or a liver or something, the cells that form that organ are strung together or hung, a bit like clothes in a wardrobe, from a scaffolding of connective tissue. So what they did was to take some hearts from dead rats and they perfused them with detergent solution. And detergent breaks open cells and destroys cells, but it won't harm this matrix, the extracellular scaffolding. So once they got rid of all the cells, they suspended this heart in a culture broth in a dish. So it had all the nutrients it would need. And they then collected stem cells from neonatal, so newborn rat pup hearts. So they got the cells that are making new hearts in other rats. And they injected these stem cells into the matrix and then just grew them for a number of days. And after 8 days, they were already detecting pulsations. So the cells were responding to local signals in the environment. They knew they had to turn into heart cells. They knew they had to grow and fill up the space. And also they found that when they injected various drugs or added various drugs that the heart would normally respond to, these cells were responding. So this says that you can use the template of an existing organ to build a new one. You can do it for something the size of a rat, but what about something the size of a human? Well, they tested that, and they got a pig heart, did the same thing, and it works. So this suggests that in future, the way in which you could get around the problem of donor organs being genetically incompatible with you would be to take your own heart out, if, say, your heart was defective, use a machine to replace it temporarily. You could then use your own stem cells to build a new heart for you, and then you could put that heart back into your body, and it would work, potentially. So there are various diseases where this might actually be very useful, like things called cardiomyopathies, where you have a genetically pre-programmed problem with the heart, where if you don't do something about it, then it doesn't work properly. But if you could take stem cells and tweak them and use them to make a new heart, you could rebuild it.
Does this mean there's instructions in the scaffold to tell the stem cells which part of a heart they should be, or is it just them interacting with each other?
Well, most heart cells are fairly homogeneous throughout the heart. There are some specialised bits, the conducting system, which funnels the electrical supply for a heartbeat down through the middle of the heart to the bottom, and so it then comes back up the outside. I don't know if they've exactly worked out how they know precisely what to turn into in what area, but one would think local triggers from the factors that are in that scaffolding probably tell them. When you put, it's a bit like hanging a sheet of material in your wardrobe, and the wardrobe then telling the sheet of material you've got to turn into a dress, and it somehow knows how to do that. So that seems to be what's happening, yeah.
Wow, quite a serious operation anyway. Having my heart taken out for a month would be
It's still amazing, because up until now no one has been able to do that. So to be able to regenerate an organ in that way, potentially, in a dish, is a phenomenal breakthrough. You could start with someone else's heart, put your own cells into it once you've got rid of all the cells, and get a new heart out at the end of the day that could replace your clapped out one. I mean, that's a phenomenal thing to be able to do, and it would be genetically compatible with you.
Wow. Now, our galaxy apparently is going to be hit by a gas cloud that weighs about the same as 1 million suns. Now, a team led by Felix Lochman from the US National Radio Observatory have discovered that a gas cloud, about 11,000 light-years long and about 2,500 light-years across, will collide with our galaxy moving about 240 kilometres a second. But we shouldn't start to worry yet. It's going to be about 20 to 40 million years until it does hit. And they think it's going to hit about a quarter of the way around the galaxy from us, so much further away than it's going to actually cause us any problems. When it does hit, though, it's going to create some cosmic fireworks. It's going to trigger lots and lots of stars to start. There's going to be lots of shockwaves creating stars. And that's not going to be too much of a problem for anyone living there at the moment. But in maybe 5 or 10 years after that, when these stars, really big stars, start to go supernova, that could be really bad and could wipe out any life in the area.
So where is this massive cloud of stuff coming from?
I think it's just a big cloud of gas, which is sort of orbiting the galaxy, and it's just happened to be redirected, so it's actually going to hit us in 20, 30,
Will it
40
hit
billion,
the part of the galaxy we're in, or will it happen to someone else and be someone else's problem?
It's someone else's problem. It's about a quarter of the way around the galaxy, so nothing for us to worry about.
Thanks. That's why it's so important to have you on The Naked Scientist, bringing us panic stories which, are not actually going to impact on us quite literally quite yet. Thanks, Dave. It's The Naked Scientist with Chris and Dave. It's our science Q&A show. Coming up later in the programme, we're going to be hearing from Mark Peplow about non-stick at the flick of a switch and other important breakthroughs in the world of chemistry. Plus, Dave's got an amazing science experiment waiting for you. If you want to have a go, you're going to need a drinking straw and a pair of scissors and yourself.
Sorting out the sparks from the quarks. The Naked Scientists. For more information, get online at nakedscientists.com.
You're listening to The Naked Scientists. Now, we've got a question for you here, Chris. It's from a guy called Istvan. He wants to know why, whatever colour of the stuff he drinks, he always pees yellow.
Okay, the stuff that makes your pee go yellow is a chemical called urobilinogen. And this is a breakdown product of the haemoglobin that makes your red blood cells red. So when you have red blood cells, they're made in the bone marrow, you have millions and millions and millions of them, and you destroy something like 10 to the 11. So that's 1 followed by 11 zeros of these cells every day. And what happens when you break down the red blood cells, which have a lifespan of about 120 days, is that the haemoglobin molecule that's in them gets split open by chemicals called enzymes, and there's a little atom of iron sitting in the middle, and the iron is released, and that can be recycled in the body. But the molecule that used to wrap up the iron, the haemoglobin molecule, which was actually responsible for binding oxygen and oxygenating your tissues, that has to be broken down even further, and it's coloured. So once you've unwrapped the iron, you have this molecule called biliverdin, and it's green, and it then gets oxidised a bit, and it becomes something called bilirubin, which is brown or yellow colour. This floats around in the bloodstream, gets picked up by the liver, and the liver adds a couple more chemicals to it to make it dissolve in water, and the liver then squirts it out in your bile, and that's why bile is yellow if you're sick. People who have norovirus problems at the moment, 3 million of them in the UK know about that only too well. But that goes into your intestines. Now, the intestines are rich in bacteria. Bacteria in the intestines chop up the extra atoms and chemicals that were added to the sides of the bilirubin molecule, and they knock off some of these other chemicals and they turn it into something called urobilinogen. And the urobilinogen is still yellow, but it dissolves in water. This gets reabsorbed in your intestines, and some of it ends up in your bloodstream. But because it goes into water, then when the blood goes through the kidneys, it ends up in your urine in the kidney, and it comes out as a yellow colour. So that's why you have yellow urine. Some of it carries on in your intestines, and bacteria change it a bit more, and they turn it into another molecule called stercobilin, and that's brown, and that's why you do brown poos.
Wow.
So there you have it. One here for you, Dave. This I'm really intrigued by. It's 2 questions on lightning, and one of them is Robert Sullivan, and he says, "Great show, I love it. I've always wondered, when lightning hits water, does it go with a splash? I've asked several of my professors, and none seem to have the answer." And Bill Geddes, on a similar theme, says, "I understand that water's quite a good insulator, and if lightning strikes a pool you're in, are you fried? And if that's the case, then how about if you're in a lake?"
I would have thought that what happens when lightning hits water, especially, is that you're somebody dumping a huge amount of energy into the bit of water that's hitting. So I expect what's going to happen very close to where it's hit, it's going to form into steam, because I know that if lightning hits sand, it gives so much energy, it will actually cause the sand to melt and turn into glass. So it's probably going to vaporise the water near where it's hit and create a kind of bubble of steam, which probably will cause a splash. Now, if you're swimming and lightning hits a lake, it is actually very, very dangerous, because if lightning hits the middle of the lake, water has got some salts in it, so it will conduct electricity a bit, but you'll conduct electricity better. So if you're swimming through the lake and there's a big current from this lightning strike flowing through the lake, and it sees you, it will suddenly see a kind of a short, that it can jump 2 metres through an easy path, so it will all flow through you. So you get a big current flowing through you, which is very dangerous, and it can stop your heart, which is why I'm sure, definitely when I was in the States, I was told very definitely in a thunderstorm you don't go swimming. So
the fish could end up fried as well then?
I guess so, yes. And I've got another question for you here, Chris. A question from Jenny Lee. She's got a class of Year 5 students and primary school, and they've been learning how muscles work. And some of the kids have noticed how they can make their joints crack, but they didn't seem to be able to do it when they'd been doing exercise. So they wanted to know what happens when your fingers crack and why exercise might affect it.
Okay, the reason you get joint cracking is because when you move a joint, the pressure in the fluid in the joint drops, and this can cause a bubble of gas dissolved in the liquid in the joint to form. And the bubble pops into existence, and when it pops into existence, it actually takes up some space. It takes up about 15% of the space inside the joint, and this causes all the little ligaments and supporting structures around the joint to pop outwards, and that's the first crack you hear as the bubble forms. And then when you carry on moving the joint, it goes click again as the bubble disappears. This is when you put the pressure back up in the joint, and it makes the bubble collapse on itself, and that releases even more energy, and that's the second sound that you hear, and it releases about enough energy, I think about 5% of the energy that would actually be needed to damage cartilage. So there's no link to arthritis if you crack your joints. Although some interesting studies done in Germany, they looked at someone who cracked the knuckles of their left hand for 35 years, but not their right hand, and there was no difference in arthritis, but the muscles on the left hand were much weaker than the muscles on the right hand. So explain that one, if you will. This is The Naked Scientists. It's Chris and Dave, and it's our Science Q&A show.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
Now it's time to do a bit of kitchen science. I hope you're ready with your scissors and your straw. Dave, what do you want everyone to do?
Well, this is a great kitchen science, although I apologise to any parents out there because I could imagine it could get slightly annoying for them. OK, so this is incredibly simple. All you do is take a straw, perfectly normal drinking straw, take one end of it, squash it a bit. So squash it a bit so it flattens it down slightly. It doesn't have to be too much. And then cut the end into a sort of triangle, maybe about a centimetre and a half long, probably a centimetre and a half long.
So you've squashed the end of the drinking straw flat between your fingers, and then you're cutting a sort of triangle out of the end of the flattened area.
Yeah, so the end looks
like you've got a V shape on the end of the straw.
Looks like a triangle on the end of the straw. Then all you do is put it in your mouth, blow, move your lips around. It should make a noise. And then, whilst you're blowing, take the scissors and chop the end off the straw a few times and make the straw
So start
shorter.
right at the end of the straw and chop a bit off.
Yeah.
And listen. Chop a bit more off and listen. And keep going up the straw.
That's right.
And what do you... don't give the game away, but what are you expecting people to kind of explain about this?
What's happening to the sound? In fact, if they want to phone in and do it live on radio, that would be brilliant. Otherwise, tell us what happened to the sound and phone in and it would be brilliant.
OK. Right, now look, we've had this really interesting question that came in. It was sent in by Barry. He's in Nottingham, in fact. He listens on the internet to us. And he's going to join us in a second. Now, he sent me this picture, Dave, which I'm going to give to you yesterday on my email address, chris@nakedscientist.com. Now, this shows a plane flying through the sky. And if you look at the picture, you'll see the usual contrail, the exhaust fumes of the plane, and then extending in front of the plane is a very long black thin line on the picture, which makes it look like the plane's about 15 miles long. It's a very thin, narrow, black line. So let's just catch up with Barry and find out how he spotted this. Barry, hello.
Hello, Chris.
Welcome to The Naked Scientist.
Thank you.
How did you spot this?
Just sitting in our kitchen yesterday, looking out the window, as I sometimes do, and obviously we have quite a few planes that fly by, and I just noticed this shadow, or not a shadow necessarily, but a different colour in front of the plane. And as the plane moved along through some, I don't know if you would agree with me, maybe it's cirrus cloud or something very wispy. As it tracked across the sky, there was this section in front of it that was darker, and it almost looked as though the cloud was dispersing well in front of the plane as the plane went along. And I wondered whether there's any way that the plane itself could be causing the cloud in front of it to disperse up to quite a distance in front of it, almost like the cloud was almost expecting it to arrive, if you see what I mean.
It's really striking, though, isn't it, Barry? Because it's making the plane look almost like a missile. It's almost jet black line, which is the same diameter as the body of the plane you can see in the picture, and it is literally miles long. So, Dave, what do you think's going on?
I just want to ask a question. Where was the sun at the time when this was happening?
Well, yeah, that's an interesting question. I mean, I didn't actually... at the time, I didn't even think about where the sun was. I was just, wanting to get the shot out of the window to get this picture. But thinking back to it, it was probably about 2 in the afternoon. So I'm expecting it was probably to the... if you're looking at that picture, which I know isn't easy on radio to imagine, but basically I think the sun was actually to the left, which would be essentially behind the plane. And because we're, I don't know, this time of year, probably quite low in the sky. So, yeah, to the left and I suspect quite low.
Yes, because what I think is going on here is that the sun's behind the plane and it's casting a shadow of the contrail. And because the sun's behind the plane, it's casting that shadow in front of the plane, as it were.
Right.
And because the cloud's so wispy and kind of tenuous, the only way you can see it is because the sun's lighting it up.
Yeah.
So you see this sort of dark. Once you're in shadow, you can't see the cloud, so it looks like the cloud's disappeared. And actually, if you look very closely above the contrail, you can actually see a little bit of the shadow following above the contrail as well.
Okay.
So I think what it is, it's just a shadow cast from an interesting direction.
Yeah. Yeah, it was just surprising to see it because I'd never seen anything like it, and I just thought, well, I'll try and get a picture of it and see what you thought of it. But I think you probably have explained it.
Thank you very much, Barry. I reckon you thought you'd seen a UFO. Sorry to have scotched that theory. But look, for everyone at home, we'll post that picture onto our forum, nakedscientist.com/forum, so everyone can see what you saw, Barry, and see why you were so surprised, because it is a very striking picture.
That sounds great.
Thank you for sending it in.
Okay, thanks.
It is The Naked Scientists with Dr. Chris and Dr. Dave. If you have any science questions for us, you can email me, chris@thenakedscientist.com. Now, last week we brought to you the first of a new series of Rising Stars. These are young Cambridge University researchers who are telling us all about their research and how it could affect the future of all of us. And this week it's the turn of a physicist, and he's Ben Colley.
The physics problems we study at school are often to do with the motion of individual objects, such as a bouncing tennis ball. But to understand the world around us fully, at some stage we have to consider the properties of continuous regions. For instance, suppose there's a long strip of ribbon lying flat on your desk. If you hold one end of the strip flat, while you turn the other end upside down, then the ribbon gets twisted, and its orientation varies continuously along its length. If you start shaking one end of the strip, then tension and speed of motion also vary along the ribbon's length. To describe properties that vary continuously in this way, we use what physicists call a field. A field is simply a statement of the value of a property at each point in a region. It could be the temperature at each point in a room, the water velocity at each point in a swimming pool, or the orientation at each point along your ribbon. Fields are especially useful for describing the world at small scales. At small scales, matter sometimes behaves like a particle and sometimes behaves like a wave, and it turns out that we can bring together these particle and wave behaviours by describing each kind of fundamental particle in terms of a field. So we have an electron field, a photon field, and so on. Each field fills the whole universe and takes a particular value at each point in time and space. If the field for, say, the electron has ripples or waves moving through it, then roughly speaking, this represents electrons moving through space. My particular research is to do with things called solitons. The name comes from the word solitary and the suffix -on, which appears in the names of particles like the electron or the photon. A soliton is a certain type of disturbance in a field, and solitons can occur in many different situations. For an example, think back to the long piece of ribbon on your desk. It starts off lying flat, you tape one end to the desk, then turn the other end upside down and tape that end to the desk too. The resulting twist is a soliton in the ribbon's orientation field. It exists because of the different orientations of the two ends of the ribbon, and you can't get rid of it without untaping one of the ends. An industrial application of solitons is in the development of superconductors, materials which have no electrical resistance at low temperatures. If you try to apply a magnetic field to a superconductor, you find that a network of string-like solitons forms inside it and affects the electric field. Superconductors are used in the construction of powerful electromagnets and might eventually be used to build high-performance electric motors, so understanding solitons could be important for developing the technologies of the future.
That was Ben Colley reporting from the coalface of research. We'll have another Rising Star next week.
Thank you, Dave. It's The Naked Scientists, Chris and Dave. In a second, we'll be talking to Mark Peplow. He's the editor of Chemistry World from the Royal Society of Chemistry. He's got some wonderful stuff for us this week, including how you can turn non-stick-on at the flick of a switch, also what Amber is revealing about Paris's tropical past, and people doing wonderful things with fish scales. But before then, Dave's in Bradwell. He's got an interesting question for us. Hello, Dave.
Hello there. I'm told I have to be very quick, so I'm going to have to run through this. I'm totally deaf. No, that's wrong. I'm 85% deaf in my right ear. Okay, and I do have a hearing aid provided by the National Health Service, and I'm told it's a digital. I don't understand the difference between analog and digital as far as hearing aids are concerned. Now, I have pretty good hearing in my left ear. Now, just through, I've been wearing this hearing aid now for about 18 months, but what I've found out through trial and error is that when I block off my good ear, I can hear nothing.
That kind of suggests that the hearing aid's not working in the ear that you've got it plumbed into, doesn't it?
I've had that tested. I have to ask my wife and anybody else in my area who are with me, is that too loud? Because my hearing aid, it boosts up the volume of whatever it is I'm listening to. And I have to juggle it. I've got 3 settings. 1, 2, 3 and 4, and also loop system and all that kind of thing. But when I close my good ear off, I can't hear nothing. So are you suggesting to me that the hearing aid is not working?
No, I'm not suggesting that. What I'm suggesting is that what could be happening is the fact that you are blocking the sound that you can hear when you put your finger in your good ear suggests that your good ear is working perfectly, and it's working perfectly for the normal way in which sounds are conducted into the ear. So vibrations in the air go onto your eardrum, make your eardrum move, and that's turned into electrical signals in your inner ear that the brain can understand. Right. Now, your hearing aid on the other side ought to be just working by amplifying the sound that you're hearing and making bigger movements in the ear on that side, so that the signals that go into the inner ear and get converted into electrical signals, even though it doesn't work as well because the signals are so much louder, what hearing is working there works a bit better, and so you can still hear things. Now, the fact that your hearing is lost when you put your finger into the other ear and block off the conduction of the sound suggests that the hearing aid is just not succeeding on that side in managing to make what's left of your hearing there actually register anything that you can physically hear. So I think that's the problem. I don't think the hearing aid's faulty necessarily. If it's been checked, it's been checked. I think it's possibly that your ear's not working as well as it could.
As quick as I can, I'm suffering, so I'm told, from Meniere's disease, where eventually I will go deaf in my other ear. And so I was thinking, I'm trying to be as quick as I can actually, if and when I'm in my mid-60s, if and when my left ear, my good ear, goes deaf, and I have a hearing aid in there, would I be able to still hear then, or would the same effect apply?
Well, it is Meniere's disease is where you don't make the right amount of fluid, which bathes the inner part of the ear. Yeah,
I am having treatment for that. I've got tablets for that.
Well, I'm pleased to hear that, because you can maybe improve the symptoms a bit, but there are various therapies that are in the pipeline now to help people who've lost the ability of the inner ear to detect sound and turn it into electrical signals. And what scientists are now exploring is the idea of stimulating the nerves that connect the inner ear directly to the brain, and you can get quite good discrimination of sounds that way. A bit like a cochlear implant, but a bit more advanced. And we'll have to leave it there. But that's basically where it's going. And there are things in the pipeline which are being tested with some success on patients who have lost the ability to hear things in the way you describe.
Yeah, cheers. Thanks a lot.
That's all right. Thanks for joining us on the programme. Good to have you, Dave. Bye-bye. If you'd like to join us on The Naked Scientist, email chris@thenakedscientist.com. It's our science Q&A show. Any science question goes. And joining us now from the Royal Society of Chemistry, the editor of Chemistry World, that's Mark Peplow. Hi, Mark.
Hello, Chris.
Thank you for coming in. Now, this looks amazing. Non-stick at the flick of a switch.
Yeah, it sounds fantastic, doesn't it? This is a group of scientists from Bell Laboratories in New Jersey in America that have created a material that switches from sticky to non-sticky just at the flick of a switch. Now, they've made this out of what they're calling nano nails, and these are, well, very tiny nails. The head of the nail is about 400 billionths of a metre across. That's 500 times thinner than a human hair. And a huge array of these nails, which are made out of silicon, coated in a fluoropolymer that's kind of similar to what your non-stick pans are made out of. Normally, liquids are repelled by these nail heads, so they bead on top. But if you apply a voltage, it actually changes the electrostatics of the nails, and it sucks the liquid around underneath each of the nail heads, and it spreads the liquid out across the surface, just as you would expect a liquid to normally spread out across any kind of sticky surface. And as soon as you take the voltage off again, the nails regain their original properties, and the water beads up again on the surface. It actually works for lots and lots of different types of liquids.
Oh, not just water?
Not just
what
water.
Sorts of applications?
Loads of liquids, sort of oils, petrol, things like that.
What could you do with this? I mean, it sounds pretty amazing. What sort of applications are being suggested for it straight away?
Well, the scientists that have worked on it suggested a couple of things. One of them is use in certain types of specialised self-cleaning surfaces. But at the moment, what they're working on is to try and use it in very miniature labs, just the size of maybe a centimetre across, called labs on a chip. They're ways of processing very small amounts of material, and they're working on using these surfaces to move liquid from one place to another in those little chips.
Absolutely amazing. We'll have to watch that space very carefully. It could come in handy in the kitchen as well. And now, take us on a trip to Paris, because you've got some interesting insights locked away in amber as to what Paris used to be like in the past.
That's right. Hey, what was Paris like 55 million years ago?
This is the city, not Paris Hilton.
Yeah, that's right. Ask a paleontologist and they'll tell you, well, it's probably a sort of tropical forest, essentially. You look at the fossil record and temperature records, it suggests that it was covered in tropical forest, surrounded by shallow seas. But chemists in Paris have found an interesting confirmation of this in amber. Amber is just fossilised tree sap, and they found a piece from 55 million years ago in Paris, and they've looked at some of the chemicals in it, and they found a very unusual chemical that belongs to a class of compounds called diterpenes. They've looked at it and thought, what sort of tree chemical could this have come from? And by doing a clever bit of chemistry, they've worked out that it came from an acid called isoosic acid. This has only really been found in one type of tree before, and it's an Amazon rainforest tree. So they're linking this as evidence to say that whatever type of tree this fossilised resin came from, it was probably a tropical tree, an ancestor of the sorts of things that we see in the Amazon today.
It was definitely growing there. This wasn't brought in from outside by various geological processes or something.
No, they looked at various different amber deposits from the Oise River, which is near Paris, and the tree that they're linking it to is called the Burundanga tree.
Sounds catchy. and finally, talking about rivers and things, fish live in rivers, and people are doing interesting things with fish scales.
Yeah, this is great. This is such a nice little story, a cool bit of detective work, really. Have you ever wondered why fish scales are so shimmery? For quite a while, we've known that it has something to do with the fact that the fish scales have crystals of guanine in them. Guanine is a chemical that's one of the information-carrying molecules in DNA. But interestingly, scientists in Israel have pushed this story one stage further. Normally, when you grow guanine in the lab, the crystals come out as a prism shape. But they actually looked very, very close up using both X-rays and electron microscopy at the guanine crystals that are found in fish scales, and they found that they were very thin plates, not at all like the prisms that you'd normally get. And in fact, more than that, the thin plates, the thickness and the separation of them is perfect for reflecting visible light.
So that's
because
why
the
fish
thickness
silver.
of it is exactly. The thickness of the plates determines how good they are at reflecting certain wavelengths of light, and they're just perfect for reflecting visible light. Now, if you look at how much energy it takes to grow certain types of crystal, it's a lot easier to grow normal prism crystals.
So how do these
in the
fish
lab.
do it?
So the fish are expending quite a lot of effort and energy to grow these very specialised forms of crystals. Now, the team that are working on this from the Weizmann Institute, they think that the fish likely has an inhibitory factor in their skin, which as the crystals of guanine are growing, it's controlling the way that those molecules stack up together, and that's what they're looking for next.
Thank you very much. That's Mark Peplow. He is the editor of Chemistry World, which is a magazine from the Royal Society of Chemistry, and they have the most amazing podcast on the Chemistry World website. If you go and give it a listen, you'll see why I'm saying that. Thank you very much, Mark. It's been great having you on the programme.
Thanks, Chris.
On the way, we'll be finding out with we'll be catching up with Chris Vallance, our technology correspondent, to find out what must-have gadgets you should have in your kitchen and living room. He's been to the Consumer Electronics Show in LA.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
Now it's time to find out the latest from the world of technology with Meera Senthilingam and Chris Vallance.
Now, the biggest event in the gadget calendar happened this week in Las Vegas. That's the Consumer Electronics Show, where all the latest gadgets and gizmos for 2008 are on show. So I had a chat with our technology expert, Chris Vallance, to find out about it. So, Chris, what's the point of the Consumer Electronics Show?
CES is really about the gadgets, about the electronics, about people showcasing their new products. The BBC's technology correspondent, Rory Cleveland-Jones, was there. Just as he was about to leave Las Vegas, I caught up with him and asked him to summarise what the event had been like for him.
We are seeing the digital home really come a step closer here through a number of different devices. Just when you think TV has gone as far as it can go, I mean, we're all getting used to the transition from cathode ray to various kinds of flat screen technologies. Now, organic LED is a new technology which so far has been used in pretty small screens. And what you get is a very slim screen, very economical in its energy use, and incredibly pure colour. It's very difficult when you see them on the TV from afar to appreciate it, but actually standing in front of them the other day, I was really impressed for once and thought, I'd like one of those. The trouble is, at this stage, it's a very, very expensive technology. I think Sony's got an 11-inch screen on sale for $2,500, about £1,300 for a tiny, tiny TV. Samsung had a much, much bigger screen. They had a 30-inch OLED screen TV, but they weren't saying when that was actually going to come to market and what price it would be. Generally, new kinds of television are a big theme here. Another TV, which I didn't get to see, but one of my colleagues was pretty impressed by, was the Laser TV, a new technology developed by Mitsubishi, again promising richer, deeper colours and lower energy use. There's a big competition here to convince consumers that they do need to upgrade yet again.
So that was BBC technology correspondent Rory Cleveland-Jones. But were there any other gadgets that caught your eye, Chris?
I must admit, one of the things about the CES, it's always fun to read about some of the weird and quirky inventions that people come out with. A couple of them, fashion models of taser stun guns. The other thing that caught my eye was an electronic picture frame. Now, you can see these things in the shops all over the place, can't you, where you put in your digital camera photos and they rotate the pictures as a slideshow.
Yeah.
There was a new take on that with a picture frame where you could actually had a mobile phone number, so you could send the pictures to it. Now, I must admit, the evil part of my brain was thinking about all the pranks you could play, or if somebody else you don't know or don't like finds out the number, could be a bit embarrassing. But lots of stuff on display at CES, so an interesting event for those that were there, and lots to be read about online as well.
So, other than CES, moving on to developments online, it looks like the people behind Wikipedia are trying to get into the search business, are they?
Yes, this is quite a big announcement. Jimmy Wales, the founder of Wikipedia, he also has a commercial business called Wikia, which is a commercial wiki hosting company. Wikia have launched what they're describing as an open source search engine. It's called Search Wikia. Well, I spoke to Jimmy Wales, the Wikia and Wikipedia founder, about the new search engine, and he told me what was different about it.
Yeah, so we're launching on Monday to have a brand new open source search engine that's completely controlled by the community of users. So it's going to work very similar to any wiki, except people will be able to participate in the creation of search results. So we're putting everything under a free license so that other people can take it and modify and adapt it and so forth. There's many different ways that people can tweak the search results. They'll be able to, at a very basic level, give thumbs-up type feedback, so 1 through 5 stars on search results, to give feedback into the algorithm. So it's very similar to, Wikipedia in the sense that the community is given ultimate control over the editorial decision.
So that was Jimmy Wales, Wikipedia founder, also the person who's behind Search Wikia, the new open source search engine.
Chris, what do you think is going to set this apart from other search engines?
The big important thing is that the search algorithm, the rules that determine what comes out on top when you type in a search term, that's all going to be open. So that's a very different approach from search engines like Google, which tend to very closely guard the exact rules that determine what comes out top of the list when you type in, soft cheese into Google. So Search Wikia's approach is very different. They're saying, let's open it all up. Let's make everything transparent. Now, that has positive effects in that, you can see what's going on, you know why things are happening, but there are other issues that then arise, conflicts of interest on the part of the people developing the search algorithm. What happens if companies see, that's how it works, so that's how we get our results further up the list. It's an interesting, different approach. It'll be, I guess, in the end, the proof will be in the pudding, and, which search engine users decide gives them the best results. But it'll be interesting to see how it develops as Search Wikia grows.
Thank you very much. That was Mira Senthillingham talking to Chris Vallance. And so they were finding out about all the kinds of things we can look forward to seeing in our living room in, 2008 or not, depending on how technologically up-to-date you are. Now, I seem to have opened a bit of a floodgate talking about urine earlier on. We had a text in, someone says, what should the colour of a healthy person's urine be, and is there an optimum colour? Well, the answer is it's all down to concentration. The more you drink, the more dilute your urine is, and therefore the more dilute any colourants, the urobilinogen that's being made and filtered from the bloodstream into it. So if you haven't drunk very much, you continue to break down red blood cells and produce this urobilinogen, and therefore you will have urine which tends to be a darker colour. Conversely, if you drink a lot, it'll dilute it and the urine goes a lighter colour. There is an exception to this, which is that if you have a problem with the bile flowing out of the liver, because you have, say, gallstones, for example, then the bilirubin, that is the thing that produces this urobilinogen in the first place, can't get out of the body, and therefore you have a build-up in the bloodstream, and this can end up producing a dark urine. So you get very, very dark, very, very dark urine under those circumstances. We also heard from Ashley, he's in Malden, and he says, why is it that sometimes when you wee, it goes frothy and has a sort of white frothy head on it? The thing that makes that happen is protein, Ashley. And sometimes if you have certain problems with the kidneys, you can produce very frothy urine. It's almost like champagne, and you get this massive head on the urine, and that's actually quite a serious problem. But the day-to-day occasional frothiness is just because occasionally there's more protein in your urine than others, and the protein breaks down the surface tension of the water, and you get these bubbles forming, and so it acts a bit like bubble bath, which is why you get the fizz.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
It's The Naked Scientist with Dr. Chris and Dr. Dave. Mike's in Hawkwell in Essex. Hello, Mike.
Hello, how are you?
Very well. What do you want to ask Dave?
If E equals mc squared, and when an atom bomb goes off, some matter is converted to energy, I'd like to know exactly what matter in the original atom bomb is converted to energy. Is it protons, neutrons, electrons, a selection of atoms? What goes, what matter disappears?
Okay, if you take a proton or something relative and make it go really, really fast, you give it lots of kinetic energy, then relativity says that it gets heavier. In the same way, if you give it lots and lots of potential energy, if you put it into a really big, heavy atom like uranium, then it will also get heavier. When you split up that big atom, it gets less potential energy, and that means that the resultants, that all of the protons and all the neutrons inside the resultants are lighter than they were before because they have less potential energy.
So potential energy can be converted to...
Yes.
So
mass is... Potential energy will give something mass as well as kinetic energy.
Right, I sort of followed that. Okay.
Thank you very much, Mike.
Right, thank you.
It's The Naked Scientist, so Chris and Dave, thank you very much for that lightning-fast answer to why things get heavier. In fact, the Sun loses something like 8 million tonnes of mass every single second just by converting hydrogen and fusing it to make helium. And so that's exactly the same process in action. Right, now it's that thing we promised to come back to, and that's all about the science of boomerangs. It's time for this week's Question of the Week with Diana O'Carroll.
Hello and welcome to Question of the Week from The Naked Scientists. This week I have a problem that I just can't seem to throw away.
Hello, this is Anand. I'm calling from Colchester, and this is my question. I want to know how the boomerang works and what's the principle behind that.
So, if a boomerang doesn't come back, it's a stick, right? Here's Hugh Hunt from the Department of Engineering at Cambridge to explain why it's not just any stick.
Oh, Diana, that's a really good question. Well, look, a boomerang goes around on more or less a circular path, and the motion is really just fantastic. It's a combination of various physical principles, for example, aerodynamic lift and circular motion. You've got to get these physical principles just right when you throw the boomerang, which explains why actually boomerangs are a bit tricky to throw. Well, now think of the two arms of a boomerang as being just like the wings of an airplane. The faster they move through the air, the more lift they generate. But unlike an airplane, a boomerang spins as it moves through the air, and the combination of spin and forward speed means that some parts of the boomerang are moving faster than others. This means that the aerodynamic lift is not uniform over all parts of the boomerang. Now, the wings of an airplane are horizontal, so the lift is upwards. But the wings of a boomerang are sideways, so the net lift is towards the centre of the circle that you see the boomerang move on. But look, there's one more important physical principle. The non-uniform lift generates a torque, or a moment, a twisting force, whatever you like to call it. And this causes the gyroscopic effect to come into play. Now, a spinning boomerang is really no different to a spinning gyroscope. And the gyroscopic effect makes the boomerang turn around nicely at just the right rate. It really is magical. And the best bit of all this is that the entire explanation rests on Newton's laws of motion. Now, there's one more little catch, and that's to do with gravity. You need a bit of lift force directed upwards. Otherwise, the boomerang will just drop down to the ground in no time. And this explains why you need to throw a boomerang with a little bit of a tilt. And it also explains why a good boomerang will increase its tilt angle as it slows down. This is called laying over, and a boomerang that is slowed down and laid over is really easy to catch.
We had another expert write in, Paul Sprague from Madison in the US. He actually makes them for regional tournaments. His top tips are A, to steer clear of trees, B, to get the appropriate left or right-handed model, and C, make sure there's a breeze coming from the left if you're right-handed or vice versa. An ideal solution for playing fetch with cats, perhaps. Why not complete our outdoor activities with a question on cycling?
My name's Jennifer, and I'm from Chicago. My bicycling club has been having a debate. All other things being equal, who goes downhill faster, a fat bicyclist or a skinny bicyclist?
Then there's another question on lift and aerofoils to solve.
Hi, my name's Kian from Sydney, Australia, and the situation I've got is there's a plane that's standing on a runway that can move kind of like a really large treadmill. The plane moves in one direction while the treadmill moves in the opposite direction. The treadmill has some sort of control system that tracks the plane speed and tunes the speed of the treadmill to be exactly the same but in the opposite direction. So the question is, can the plane take off?
So if you know who you'd back in a sloping cycling race, or if it would be wise to minimise Heathrow Terminal 5 with the installation of a treadmill, then send your thoughts to questionoftheweek@thenakedscientist.com or pop into our forum at thenakedscientist.com/forum.
Thank you very much, Diana. So the physics behind the flight of a boomerang is actually pretty simple, even if you don't manage to throw it quite as well as the guys down under. Now, who would go faster in a bicycle race downhill, a fat person or a thin one? If you want to do the experiment yourself, then do let us know. We'd love to know the answer. And would a plane take off if it was on the aeronautical equivalent of a massive treadmill? If you've got any thoughts on that, then drop us a line. Question of the week at thenakedscientist.com.
Laying the facts bare. The Naked Scientists.
It is The Naked Scientists with Dr. Chris and Dr. Dave. If you have any thoughts, comments or questions, then you can get in touch with us. Email chris@thenakedscientist.com. Now take a listen to this.
Sorry.
That works well, Dave.
It was always on live radio. You can't get them to work.
What about the other one? Does that work?
I tried a different one. This one was definitely working before.
OK, so just so that people don't think Dave's going totally mad, what he's actually doing, he's got a drinking straw. We told you earlier to cut the end of the straw so that it forms sort of triangular spike at the end of the straw, and then blow down it, either end of the spiky bit, and then slowly reduce the length by cutting it with a pair of scissors. And you heard the result there. Why is that happening? What's going on?
OK, the first question is, why is this making any noise at all? What you've done is you've actually made a reed instrument. It's very like an oboe. You've got two triangular pieces of straw that's hanging off the end of the straw, and they're kind of quite flexible. And when you blow through them, if you get it right, that's actually when the air's going really fast through them, and that actually reduces the pressure of the air, so it sucks the two of them together. As it sucks the two of them together, they'll get and they suddenly close off, and that suddenly stops the air very suddenly. All of a sudden, it's not moving anymore, so there's nothing to suck them together, so they open again. The air flows through, then stops.
Oh,
and
it goes in fits and starts, and the two spiky bits vibrate.
Yeah, the two spiky bits vibrate, opening and closing, and letting
that's
the air
how the
through
reed of an oboe works, is
That's
it?
how the reed of an oboe, in fact, the same as a saxophone, all that kind of reed instruments work like that.
And what about the business with cutting the tube? Why does that reducing the length of the straw make a difference?
Well, the actual sound which the reed makes is a whole mixture of lots and lots and lots of different frequencies, lots of different pitches. Now, the length of the straw affects which ones are amplified by the straw. The sound waves kind of go down the straw and they get reflected by the hole at the end, and the waves go backwards and forwards up and down the straw. I don't know if you've ever played in a bath when you're kind of sending a wave up and down the bath. If you send another wave down in time with one which is coming back, you can get that wave to get bigger and bigger and bigger.
You can have tsunamis in the bathroom, and I used to do that when I was little and flood the kitchen underneath. Just get into all kinds of trouble.
Something very similar as I was a kid.
All in the name of physics.
Indeed. And the longer the straw is, or the longer the bath is, the longer it's going to take for that wave to go backwards and forwards, so the lower the pitch.
Oh, right.
So
okay.
as you cut the straw off, it's like making the bath shorter, so it's quicker for that wave to go backwards and forwards, so it's quicker vibration that's amplified, and so it makes the pitch higher.
And so when you have an oboe that you're playing, you make different pitches and notes by covering and uncovering different finger holes. So why... Obviously, you don't want to chop the end off your oboe because that would be expensive and the instrument wouldn't last very long. So why does having the finger holes make a difference to the notes?
Doesn't need a very big hole at the end to change the effective length of the tube. So even if you just make a little finger hole, if it's in the right place, that can effectively make the tube much shorter. And so it's like cutting it off and cutting it up, but rather cheaper.
Okay, and so the other applications of this kind of technology, where do we see this in the world around us?
The changing the length of the straw in basically all woodwind instruments, and in fact, if you consider it slightly more widely, the lengths of a violin or something, the longer the string, the lower the note, in a similar sort of way.
So there you have it. You heard it on The Naked Scientist, how to make your very own oboe and the principles of how things that involve tubes make notes. Right, if you want to catch up with more kitchen science, there's loads of experiments like that. They're all on our website at nakedscientist.com/kitchen science. Dave writes them all up assiduously every week. Lots of pictures of him making a fool of himself and bits of video as well, so you can go and drop in and see that. Here's a question for you, though, Dave. Jeff Ostiff says, do you weigh less at the equator than at the poles because of centrifugal force on the rotating Earth?
Yes, in fact you do. Although your mass is the same, so you've got the same amount of fat, the same amount of you. When you're at the equator, you're spinning round, so you're getting thrown away due to the centrifugal force, the same sort of force if you've ever sat on a roundabout and it's spinning around, you can feel yourself being pushed away from the centre. It's actually, you're even lighter than just the centrifugal force would give the impression of, because the Earth actually bulges out at the equator, so you're further away from the centre of the Earth. So you're actually even lighter, even if the Earth wasn't spinning, than you would be at the poles. So
if you were going to buy something, it would be better to buy it at the North Pole because you get more weight for your money than if you bought it at the equator.
You'd actually want to buy it at the equator because...
obviously, if you're buying, if you're selling, you want to be selling at the poles and you want to be buying at the equator. I had a similar question a little while back, which I was sort of debating with some people, which was, how much less do I weigh whenever the moon is directly overhead, because the moon's a gravitational pull on me, pulling me away from the Earth. So when's the best time of day to get weighed, I guess?
It will have an effect. I think it's very, very tiny.
I think we calculated it's something like 0.48 grams for a 100 kilo person. They're going to be about half a gram lighter when the moon is directly overhead, because the moon attracting you in the same way as it does water when it makes tides.
Cool. And I've got a question here for you, Chris. This is from Duncan Smith. He's been wondering about saliva and where it comes from. Is it just filtered out of the blood in a similar way to your kidneys?
Yeah, it is. You make saliva in the same way that you make tears. You have glands which have a rich blood supply. When the blood goes through, it passes through very thin-walled capillaries, which are a little bit leaky. And it's exactly the same as if you go to the garden centre and you see those watering systems where the pipes have small holes in them, and you turn the tap on, the water going through squeezes some of the water out of the pipe. Now, why do you make saliva, and in other words watery liquid, and not blood come squirting out? The answer is that the holes in the walls of these tiny capillaries are just small enough for water molecules, but they're too small to let the bigger protein and cellular components of blood leach out. So some things can get out, the water and some antibodies, but that's about it.
He was also wondering whether it would stop viruses as well.
Saliva does, because it's got antibodies. It's got an antibody called IgA, which is one of your immunoglobulins, which can neutralise viruses in it. So, yes, you can mop up a lot of colds and other viruses and bacteria with the constituents of saliva.
And they wouldn't get through from the blood either?
The antibody is secreted. You actually have a pump on cells which push the antibodies into the saliva. So they're added after you've made the saliva or the tears.
OK, cool.
Thank you very much, Dave. Right, well, that's pretty much it for The Naked Scientist this week. Thank you for joining us. We're back next week and we'll be exploring the science of how we actually mitigate the effects of global warming. You've heard about rising carbon dioxide levels. What can we actually do to get the levels down again? We'll be hearing how someone's trying to lock it away in lava, amongst other things. Thank you very much to our production team, Diana O'Carroll, Ben Valsler, Petra Minch, Mira Synthillingham, and also our guests this week, Chris Vallance and Mark Peplow. Have a great week. See you next time.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.